today we're entering into new territory, section 5.1 area. I don't really like the way the book goes about this, so came up with some material on my own that I thought was a little more useful. I'm not a historian, but I think the idea of area, it has to be more than 4,000 years old. Probably relates to agriculture. A farmer, and you want to negotiate with someone for a field somewhere. You're going to grow crops or you're going to graze animals. You need to know. You need to know whether a piece of land that's 100 feet by 100 feet is more than, say, 200 feet by 60 feet or whatever. So, along with general development of mathematics, we need an area and the idea of area. Most of what we know about area was already known by around 300 BC by the Greeks and written down by Euclid in his treatise. I suspect most of you took geometry in high school, so you'll know most of what I'm going to talk about at the beginning. But the idea of area starts with, we start with length. And we have the idea that you have a square, equal sides of the length one, and this is a 1 square unit. An area. Well, okay. Pieces of area can add. So we can extend this. We have a rectangle that's, say, 2 by 3. We just extend this idea of multiplying the length times the width, and we have something with the area of 3, area of 6. So, okay, so we've got the area of a square, is the side squared, and the area of a rectangle is the length times the width. At this point, the question comes up, well, how do we find the area of a triangle? And it turns out there's a very, very simple idea you can use. In any triangle, embedded in a rectangle, and you can see by symmetry, we'll just call this piece 1, piece 2, that the area of the triangle is just half the area of the rectangle. So that gives us the formula for the area of the triangle as base times height divided by 2. And once we know the area of the triangle, pretty much any polygon we might have is now, we can now go after it. We can just divide it up into triangles and find the area of each individual triangle. All right, so much for the area of curves or enclosed areas where the borders are straight lines. But of course, we also want to think about area inside of the curved. It's a perfect circle, isn't it? Let's see if I can do a little better. So, first object we want to think about is a circle. And we can divide up the circle into kind of pizza pie pieces here, like so. And each of these little pieces of pizza is itself a triangle, or approximately a triangle. As we increase the number, the base gets flatter and flatter, and we get closer and closer. So we can take each of these triangles, triangle 1, triangle 2, triangle 3. So triangle 1 is just 1/2 the radius times its base. And I'm not going to write this down very well. We basically can add up the area of these triangles, but the total base is going to approach the circumference. And the circumference we know is 2 pi. So using our triangle formula, we know that the area of the circle is going to be what? It's going to be the circumference, 2 pi times 1/2. I'm sorry. Circumference is 2 pi r. So 2 pi r times 1/2 r, or pi r squared. So that's one way we can look at the area of a triangle. So much for the area on objects that are flat. So what do we do if we have something that's not flat, it's a cylinder? Well, you kind of cut the cylinder. You kind of unroll it. Unroll it and flatten it out, and we start with a height and a radius. We know the circumference of the radius again is 2 pi r, and then we just have a rectangle, so it's 2 pi r h. So we can take something that's not flat and we can flatten it. That leads us to the last of this progression here. We have a sphere. Does anyone recall if I have a sphere whose radius is r, does anyone recall the area of a sphere? You recall this from high school geometry? You can't do this trick that you can do with a cylinder with a sphere. You can't flatten it out. Whenever you see a map of the whole world, they have to do something to distort it in some way. They either put cuts in it or they change the scale. But there's no way mathematically to take, a spherical surface and make it a flat surface. So we don't really have, based on what we've done so far, we don't really have a way to determine what this area would be. The formula is 4 pi r squared. We're actually going to be able to develop this using calculus. But this was known to the Greeks, and they had a method that was called, it's just a funny term, it's called the method of exhaustion. Like you just get exhausted doing it, I guess. Which is not that different from what we do today in calculus. It's not as rigorous, but it allowed them to determine the areas and lengths of various odd objects. Okay, that's most of the background I want to give you. There's one more formula we're going to need, so I will bring it up. We have a trapezoid. What's a trapezoid? It's a quadrilateral with technically exactly one set of parallel sides, although it's kind of a degenerate version would be a rectangle. And it has 2 bases, an upper base and a lower base, and a height. And one way to think of the area is the line through the center, we know from geometry, is just the average of the 2 bases. And you can think of the area as that length, E1 plus E2 over 2 times the height. That's our area of our trapezoid. So we're going to use that. So I wanted to bring that up in case you weren't familiar. If you wanted to develop this, it wouldn't be that difficult to simply pull down a perpendicular, and now we have a rectangle and 2 triangles. So we'll have to kind of work out how we get this formula for that, but it's not crucial. Okay. There are a lot of people who came in late. I want to just take a minute to turn some homeworks so we don't miss out. Still kind of short on people. So, as I said, I wasn't that thrilled with the way the book approached this, and I went ahead and I looked at a few other calculus books, and I noticed they all seem to think that this idea of a very general area as being something very almost impossible to explain or to conceive. And I thought about it, and it seemed to me that it's not really that difficult an idea. It may be difficult mathematically to describe it, but my idea was, well, let's take a dish that's maybe a square dish, maybe a thin layer of liquid in it. And, you know, we know the volume. We can, we have a psi of S, and height of the liquid, we have a volume, which is S squared H. Well, if we have some other kind of odd-shaped area we're kind of wondering about, we could do the same thing. We could kind of fill it to the same height with some liquid. And we could look at its volume. And we compare the two volumes. We can do that with a volume of liquid. And we can come up with, you know, some idea of what the area of this surface area is of this odd-shaped object. Again, it's not so easy mathematically. We have to, we have to dig a little deeper, but conceptually, it's not that difficult an idea. All right. So I'm going to introduce you to the most fundamental way we want to think about area in calculus. This is kind of a building block that we're going to use. We're going to be able to extend this to various shapes of areas and also to volumes. We start with this idea of we have a function, some f of x, and now for the time being, think this is a continuous function. It actually doesn't have to be continuous. It does have some constraints on it, but for now, let's just think of this as a continuous function. And we have 2 points on the function, A, and this point here is going to be f of b. And we're interested in the area between these 2 points below the function. That's kind of our job to kind of investigate how we might determine this. So what we're going to do is we're going to take a look first at just some specific piece of this. 2 points that you can think of as close together. I'm going to give them the names xn and xn plus 1. And we're just going to approximate this area as a trapezoid, where these 2 lengths are the bases, and xn plus 1 minus xn is going to be the height. So this area of this, I'll call it just a section, is what? It's the 2 bases, which are f of xn plus f of xn plus 1 over 2 times the height, which is, as I said, x of n plus 1 minus x of n. And we're just looking at the area of this slice here. course, we're not interested in just this area, we're interested in the entire area. So we can, again, divide this up into a number of these trapezoids. Okay, and we're going to label A x of 0. And what do we want to label B? I'm going to label B x of capital M. And we're going to start adding these trapezoids together. So our area is area of F between, I guess I shouldn't have used A, should I? A and B is what? Well, the first trapezoid is F of x0 plus F of x1 over 2 times x1 minus x0. And our next trapezoid is F of x1 plus F of x2 over 2 times x2 minus x1. Keep going, we add all these up. So we get to the last item. That would be F of x capital M minus 1 plus F of x capital M over 2 times x sub M minus x of M minus 1. Now, up to this point, this is actually the correct way to do this. We're going to diverge a little, as is traditional in calculus classes. We're going to diverge in a direction which is not the right way to do it, but it's the way they always show calculus students. What we're going to do is we're going to assume each of these distances here is the same. We're going to call it delta x. So, kind of erase this, call this delta x. And I can erase this and call it delta x. So now, I can factor out this delta x. And in fact, I can factor out a delta x over 2. So I get delta x over 2 times f of x0 plus f of x1 plus f of x1 plus f of x2 all the way over to f of x m minus 1 plus f of x mod m. Now, a digression on delta x. Well, how many of these sections do I have? I started at 0 and I went to capital M. So I actually have is that right? I have m of them. But the distance from A to B is B minus A. So if I divide that by m, That's my delta x. So I end up with a formula that kind of looks like this. It's p minus a over 2m. So I keep my 2 here. And then I'm going to sum from n equals 0 to m, the sum of f of x of n plus f of x of n plus 1. So now I have a sum which describes the area as the sum of all these pieces. And now what I want to think about is the limit as n gets very large. In other words, I want to look at the limit as n goes to infinity. That is, I break this up into finer and finer sections. And now let's think about what a limit is again. All right? Limit is a number that we're going to get closer and closer and closer to this idea that we want to call the area. Right? We always have trapezoids, right? And this is a smooth curve, so no single trapezoid is exactly right. But we're not worried about actually being the actual value. We just want a number that we get closer and closer to. And that's what we're going to call this area of, I'm just going to call it F. Well, how would we calculate this? If we're not doing the abstract mathematical thing, we're just trying to measure something and we want to get an area. We don't have to go all the way to infinity. We just have to get m large enough that the error we're looking, or less than the error we're looking for. And if you think about it, this kind of operation is precisely what computers are good for. And in fact, I don't know if we went over this, but you have one of these TI calculators, and you have a function, and you use the Calc menu. You'll notice number 7 on these has this funny symbol we're going to talk about. Has this symbol f of x dx. That's precisely what a calculator does. It takes this sum, uses a very small delta x or a very large m, and just adds all these up and gives us an answer. All right, I'm going to stop for a few minutes now. No, it's a little early. I'm going to take a break, and we'll start again in about 5 minutes. curves, isn't that right? Yeah. I have to take my mask off when I drink this. During this interlude, I'm just going to mention I have two papers done in graph paper without a name. They have good grades, and then you have one that isn't. So, with a provisional statement here, what I'm going to say next is not strictly correct. We're talking about higher level mathematics, but for our purposes, it's perfectly usable. This kind of structure here, this sum taken as a limit, we have some notation that you may have seen before. It looks like this. We have this large curly symbol, and the A and the B here, put a function here, and we put this thing here, dx, and I'll talk about this a little. This is notation, all right? This big curly symbol is intended to be kind of an S, meaning sum. But it of course doesn't mean a finite sum, it means this limit sum, this infinite sum. We put the two limits here. We're going from point A in the function to B. And this dx here is notation. You can think of it as, well, we're taking the function and we have a little dx here, infinitely small dx. This notation is from Leibniz. You may recall for the derivative of a function we have dy dx. And you can think of these dx's as kind of the same kind of animal. Again, they don't symbolize a real quantity, they're just a notational device. So this is our symbol, for this this limit, which is going to give us an area. I should note that the x here is what we call a dummy variable. It doesn't really matter what it is. If I wrote f of a to b of f of t dt, it's exactly the same thing. When we're done figuring out what this area or quantity is, the t is no longer part of it. And in particular, I want to say that this object here is a number. It's not a function, right? It's a number. although, one whose value you need to calculate. Right. I'm gonna sidestep this for just a minute. Is there anyone in this class who's taken statistics? Okay. Have you run into this function? Or maybe you might have seen it as this. No, okay. It's interesting. All right. If I were to draw the function, would you recognize this? Yeah. Okay. This is called a normal function, or sometimes it's called the bell curve. And it's very important in statistics. We're not going to do much with it here, but I bring it up because when you're doing certain kinds of statistical tests or calculations, what actually becomes important is the area under this curve. I'm probably going to leave it at that, but the important point is that while you will see we have ways of calculating these objects for many functions in a very direct way, with this particular function we don't. So we're really limited to, again, using a calculator and having the calculator calculate these values. All right. So if you happen to have a calculator with you, you might want to take this out and follow along just for practice. We're going to do an example. I'm going to do an example here. Function is f of x equals x cubed plus 2x squared plus 5. And what we want to find is the area under this curve from 0 to 4. So again, you take your calculator, and if you don't have one, you're sitting next to someone, maybe take a look at what they're doing. You press the y equals button, and you put in the function x cubed, which again, recall that the x has to be this button next to alpha. So x cubed plus 2x plus 5. And then just to see what we've got something reasonable, it's a good idea to hit the graph button, see what the graph looks like. So I'll repeat this here. It looks like this. So when we're looking from 0 to 4, we're finding an area over here. So the way you get the calculator to do this for you is you hit the second calc button. You press 7, which again has that funny symbol. And the first thing you have to enter is the first number, which it seems to default on mine to 0, so I can just hit enter. And then you enter the next number, which is 4. Hit enter. And then you wait, and it actually shows you it's like filling out the area here, and comes up with what it says on the bottom. Integral fx dx equals 100. That's nice. Kind of satisfying. It seems like whatever approximation it did, it came out with a nice even number. It's probably exactly correct. Right. I'm going to do another problem. This time, I'm going to let someone from the audience tell me what they get. The function I want to look at is sine of x. And I want to calculate from 0 to pi of x dx. Make sure you have your calculator in radian mode, because we're doing radians. And if you go ahead and try that. Have a value yet? I guess I should note, when you get to that stage where you're entering the A and B, you can use the pi symbol on your calculator. You don't have to type in 3.14 or 159, etc. Anyone come up with a number yet? Let's see, how long does this take? I'm done. Does anyone else have a number? Yes.
2 pi. I got 2 pi.
2 pi.
2 pi.
You get 2 pi.
6.283.
Okay, so this is just a operator error. Okay. 2 pi is where we're going from here to here. If you hit 7, the one with the little symbol here, you should get a different number. Anyone get something different? Yes.
I had 0, but I have no idea.
Yes. You got the right answer. 0. Why is that? Well, I'm adding little trapezoids over here. But the trapezoids over here, the values of f of x are all negative. And in fact, when we're using this symbol, area, when the function goes below the axis, this is all going to be negative area. If that's not what we want, we can do something about that. We could change what we're doing here from 0 to 2 pi of absolute value of f of x, which our calculators are capable of doing. But all the area here completely, negates all the negative area here, so you get 0. All right. One more kind of calculator problem. That was. I don't want to erase this. It's actually the function I want to work on here. If I could take f of x equals e to the minus x squared, you have to enter that kind of carefully and find a value, say from -5 to 5. Just type it in. So give that a try. And see if you can come up with a value. Yeah, this is kind of tricky. You have to make sure the calculator knows what you want. Do you enter that? You need e raised to something. Minus x squared. This is where if you have one of the newer calculators, it's a little easier because you can, instead of writing it like this, they're going to actually put negative x squared. But the key is you want to, you probably can't see this, but you want to make sure that the graph kind of looks like my graph over there. And calc, when you say 7 minus 5, those are just calc 7 performing. Has anyone ever been able to get him to do this? Okay. So what number did you get?
I got 1.47 times 10 to the 10.
Okay. And can you,
Wait, sorry, 1.47 times 10 to the 10. Times 10 to the 10.
yeah, again, there's some kind of operator error here. Try one more time here. These things, I did this, I tried this before I came to class. And it worked just fine. But now I have something that doesn't like. Oops, now I screwed myself. Okay, E raised to the, I'm going to try this. -1 times x squared.
So I put the equation wrong, but into the negative x squared.
Oh,
See,
okay.
So,
All right. Well, I'm giving it my next try here.
Professor?
-5. Yeah, it won't let me put in a -5. All right, I'm going to try.
Professor?
Yep.
We got 1.77.
At 1.77. Okay. Now, here's what I want you to do. I want you to use the second answer key. I'm going to get out of the graph and square it. You know how to do that? Need a drum roll here. Did you square it? What did you get?
3.1415. Basically pi.
3.14.
15.
Oh, does that look familiar? Yeah, this is one of the mysteries of mathematics. I use -5, but by the time you get to -5, the rest of the area is so small it doesn't really matter. If you were to calculate the area out to infinity, you get the square root of pi. That's actually a very hard problem to prove, but and we will not do it in this class. All right. I guess I only have a little bit more to say. We're gonna continue on next week, looking into this object. This is called an integral sign. And this construction where we have two limits, this is called a definite integral. And again, I am repeating myself because it's important. A definite integral is a number. It's not a function, there's no variables, it's just a number, once you calculate it out. All right, class is a little short today, but I am here for the rest of the class to host a review session. If you have questions, homework questions, if you want to go over anything on the review sheet, I'd be happy to come. And, if you're not interested, you may go, but your choice. We are prepared for the midterm. want to